one of the goals of our definition of linear dependence was capturing this idea that one of the vectors in a spanning set was actually somehow redundant and didn't affect the span. But we haven't actually checked that we've captured that feature of dependency or redundancy, so let's actually check. So here's what we want to check. Let's suppose that we have some vectors that are linearly dependent, v1 through vk, and just to be explicit about which one of these is redundant, let's say that it's the last one, vk, that's a linear combination of all the previous vectors. Then what we're hoping, what we were intending to capture with this idea of linear dependence is that in this situation, vk is sort of the redundant one, and so we can actually drop it from our list of vectors without changing the span. So I actually need a -1 right here. There we go. Now it says what I meant for it to say. So the span of all of the v's is actually the same as the span of all of them except the last one, right? This is really saying that you didn't need the last one. It was somehow redundant. So let's check that this is the case. Well, because all of the v's up to the k minus first one are in the list of all of the v's, it's clear that the span on the right is contained in the span on the left, right? Any linear combination of v1 through vk minus 1 is also a linear combination of v1 through vk, and so everything in the span on the right is in the span on the left. So really the only question is the other way, is this containment true the other way around? Is it true that every vector on the left is also in the span on the right? So let's take a vector on the left-hand side. A vector on the left-hand side would be in the form a1 v1 plus ... all the way down to ak vk. And what we need to do is somehow write this as a combination, but a linear combination of all but the last of the v's. Well, we said that these v's are linearly dependent so that vk is a linear combination of the previous v's. Well, that means that v sub k is a linear combination of these v's. So it's b1 v1 plus ... down to bk minus 1 vk minus 1. So there are b's that make this true. Well, what we can do is just take this expression for v sub k and plug it in over there. We get a1 b1 plus ... plus a sub k minus 1 v sub k minus 1 plus a sub k times, and now we plug in our big expression for v, b1 v1 plus ... plus b sub k minus 1 v sub k minus 1. But now we can combine like terms, right? There are two terms in this big sum with v1. The first one is just a1, and then the second one is ak times b1. So plus a sub k times b1, and that's all times v1. And, you know, there's something similar for all of the other v's, all the way up to v sub k minus 1. And let's see, the first coefficient is a sub k minus 1, and then there's a term with a sub k times b sub k minus 1. But this vector clearly is in the span of v sub 1 through v sub k minus 1 because we've just displayed it as a linear combination of these spanning vectors. So this demonstrates the containment the other way, so which means that these two spans are actually equal. So this demonstrates that we really have captured the idea that when you have linear dependence, you have a redundant vector, and removing that vector from your spanning set doesn't actually change the span.